All right. Hello again. So again, my name is Joey. I'm one of the teachers here at OneClass, and I'm just going to do a little introduction about myself before we jump into everything. Amidst the entire COVID situation, we have a lot of students who are now at home, who are some of them actually expected to learn from home. So what we're doing here at OneClass is we are offering free lessons in both mathematics and in chemistry, so to make sure that we get our students caught up in terms of material and that they are ready for school whenever that starts. My name is Joey, and I'm going to be this is trigonometry and calculus, or for some of you, pre-calculus. And today we're just going to go over a specific, what we're going to cover in our unit today. And what we're going to do is we are going to start the course officially. So I'm just going to switch my screen right now. So what I'm doing here is, I know some of you might be familiar with this website. This is CUDA software, and what we're going to do is we're going to go over all of these, basically all of these worksheets. So we're going to, I'm going to help you with functions, power, polynomial, rational functions, exponential and logarithmic expressions, and trigonometry. And there's some units here that are part of calculus and vectors that we might touch, but these four are the real the meat and bones of pre-calculus here. So we're going to start off with functions, and today we're going to talk about continuity. So just before we jump into things, just a little bit about myself. So my name is Joey. Again, I'm currently a faculty of education teacher candidate at York University. I'm going to be graduating hopefully in June with my certificate in high school, in teaching high school science, or high school science as well. But I'll be qualified, hopefully, fingers crossed, to teach math in September as well. So that's just a little bit about myself. I'm really passionate about STEM, and I hope that if you're watching at home, for all the viewers home, that you'll be able to learn with me as well as we go through this journey in pre-calculus. So let's just get started. So in the first unit of pre-calculus, we're starting with functions. So a lot of you should be already familiar with functions and what they entail. Maybe in your previous math course, you've done already stuff with you're definitely already familiar with terms such as polynomial functions, specifically quadratic functions, and maybe higher degree functions, maybe a cubic or quartic function you might be familiar with. Rational functions were a big thing as well, exponential functions, there might be square root functions, absolute functions as well. So a lot of these various types of functions you should be already familiar with from your previous math course. If you are not, I encourage you to definitely just check out some YouTube videos and kind of get caught up, or definitely check out one of our other courses to kind of catch up on what those functions entail. But I'm just going to jump right into it. So today we're going to tackle this topic of continuity. So I'm going to write this down real quick. So this is a topic of continuity. And basically what that entails is it's determining whether a function is continuous at a specific point. So whether, I'm going to say f of x as my function. Function is continuous at basically at any point, or it could be at a specific point, or specific point and or at x. So a lot of times functions that you're already familiar with, such as let's say for example, I'll just do a little graph here. Sorry, that was really messy. For example, you're already familiar with this function here. We all know that this f of x, this is y equals x squared. And as you can see here, for every there's in this function, it's all continuous at all x's, because sorry, I drew my parabola really badly. It's supposed to touch 0, 0. So it's supposed to be like here. Yeah, it's a really bad parabola, but you get what I mean. But it's continuous at all x's, and what that means is because I don't get any type of algebraically, I don't get any things such as if I'm dividing by 0, or if I get something that reaches infinity or something. At every x, if I sub in a x value, for every x there will be a y. So every time I plug in something algebraically for my x, I'm going to get a y value. And if you look at the graph like if you look at it graphically, I'm going to get a point at every x. So if it was a negative x value, I would get something in this region here. And then if I get something that's positive, I would get something that's in this region. So this is positive, and this will be my negative region. So for every negative x, I have a function, or it's gonna be a positive value in this case. But for every positive x value, I'm gonna get a positive number as well. So in this case, my f of x is continuous at all points. So that's kind of just the definition of continuity. Continuity is important because a lot of functions that we have discussed before, like such as rational functions or piecewise functions, a lot of them have some sort of discontinuous point, and that's what we're very, very curious with discontinuity as well. So let me write this down. So this topic of discontinuity. So when f of x is discontinuous at most of the times it's at a specific point, specific point x. So for example, and there's actually multiple types of discontinuity, but I'll give you a general kind of I'll give you a function that you're already familiar with first. So we have the function, if I take, for example, if I take y equals 1 over x, we know how to graph this. This is the simplest kind of rational function you have. So I'm going to graph this real quick. And this is just a quick sketch. It's not very accurate. So here we have y equals 1 over x. And as you can see here, as you might have learned from your previous math course, we learned about this topic of vertical asymptotes. And I'm going to write this down because this is important. So vertical asymptotes, or VA. It's just short form for vertical asymptotes. And vertical asymptotes, what they are, is that they are they're a region or some sort of algebraic expression that does not, that the function cannot exist in. So for example, if I plugged in x equals 0, so let's do this in black. So at x equals 0, y equals 1 divided by 0. We know that we can't divide by 0 in math. This will get us, if you plug this in your calculator, this will give you a math error or some sort of error. So what that is if you look at it graphically, if at x equals 0, it's at this point, is at this line here. But we're going to realize that y equals 1 over x does never, ever touches x equals 0. So in this case, this is my vertical asymptote because it's going from up to down. So vertical asymptote in this case is x equals 0. And what that is that if we try to plug in x equals 0 algebraically into our function, we don't get a specific value for our y. So in this case, if you look at it graphically, because it's a vertical asymptote, it's a line that never reaches its x equals 0, just because it reaches infinitely towards it, but it'll never actually touch that region. So and this is, we're hovering this topic of calculus when we talk about kind of infinitely approaching stuff, but we'll kind of go over that as we move on in terms of math. But you should be familiar with this function already, y equals 1 over x, and that it's discontinuous, or we can say in your previous math course you would have said a vertical asymptote exists at x equals 0. But in pre-calculus, what we can also say is that we can say that f of x, or y equals 1 over x in this case, is discontinuous at a specific point, and this point's at x equals 0. And this is actually a type of discontinuity. This type is called an infinite discontinuity. So let me write this down. So infinite discontinuity. And what that is it goes towards, graphically, you see it goes towards positive or negative discontinuity, or negative to or positive infinity. And how I see it graphically is that it's kind of a vertical asymptote or a horizontal asymptote. So in this case, I have a vertical asymptote, and it's going towards this guy here. I'll do this in red. This guy here is going towards a positive infinity. It's going towards positive infinity, and this guy here is going towards negative infinity, which means it's an infinite discontinuity. So it's heading towards infinity. If you had a horizontal asymptote, and you actually do have a horizontal asymptote in this case, you have a horizontal at y equals 0 as well, which is this guy here. as you can see, these points head towards negative infinity, and this point here heads to positive infinity. These are all parts of infinite discontinuity. So again, in your previous math course, what you would have, what you would have gotten is you would have written horizontal asymptote equals y equals 0, vertical asymptote equals x equals 0. Okay, so that would be it. But in this case, what we can say is y equals 1 over x has an infinite discontinuity at x equals 0. So we can say it has so it's infinite discontinuity. So I'm gonna write this down here. This is infinite. Sorry, I'll scroll up so you can see the stuff I wrote here. So infinite discontinuity at x equals 0. And you can say it at y equals 0, but in this case it doesn't really matter. We're more concerned with the x values in this case. So that's an example of infinite discontinuity. So I'm going to define this for you. So let's say, if f of x heads towards this is positive infinity or negative infinity as well. So that's just the definition for infinite discontinuity. And what other stuff we have is we have different types of discontinuity. So for example, this is infinite discontinuity, and then we also have we can also do a removable discontinuity. So I'll write that down. There's removable discontinuity. Removable discontinuity, what that is you can in algebra we can say it's a hole in our function. So if you look at actually this little exercise here, I'll zoom in for you. At this function here, you see a little like circle with a hole it's kind of like a little hole. It's a circle in a graph. This here is called a hole or a removable discontinuity. And basically what that is if I were to sub in my x value in this case it's x equals 0, it's going to not give me an f of x. I cannot. It's just a removable discontinuity. It's a hole in our function. You could say. So I'll write here. This is a hole in our function, and that in the sense that if I were to plug in I'll say f of a in this case, where a is the x value. Actually, I'll just do f of x, where f of x does not have a defined value. So what that is again, if I sub in f of x, if I sub in a specific x value into my graph, and there happens to be a hole in the graph, this is called a removable discontinuity. It's easier to see it graphically. So as I showed you in this example here, this hole in our graph means that it's a removable discontinuity. So that's another type. And our last type is that we have something called a jump discontinuity. So this is jump discontinuity. That's a P, sorry. So jump discontinuity, and what that is, and this basically only exists in a piecewise function. And remember, a piecewise function is a function that's kind of divided into two parts depending on which x values you have. So you could have multiple functions within one function. So if you look over at kind of example 6 here, this is example of a piecewise function. And actually, I'm going to take this example because this is actually a great example to explain what jump discontinuity is. So it says here f of x is negative 2x when x is less than 3. And then we have here f of x is negative x squared plus 8x minus 16 at x equals 3, or this is greater than 3, and then negative 2x is less than 3. So we have kind of two parts of this function. We have, we know that this is a linear equation at the top if x is less than 3, and we know this is a quadratic equation if x equals 3 or is greater than 3. So a jump discontinuity just means that it's kind of like a removable discontinuity, in the sense that there's also a hole when you have a specific x value, but what it does is we call it a jump in math, and it gives you another function. So I'm going to graph this because it's actually much easier to see it when you graph. So actually, I'm going to graph this out. Actually, this is negative 2x at x is greater than 3. So maybe I'll just do a little sketch. So this is at 3. I'm going to sorry, this is negative 3. Sorry. So maybe this is at 3. And then I have a linear line that goes towards, it's a really bad line, linear line that goes towards 3, and then afterwards it becomes some type of function. So it goes maybe something like, maybe something like this as a parabola. It's just a little sketch. It's not what this graph is, but it's just a little sketch about what this could be. And what this is again, we have two functions together, right? We have, and I'll show you, we have, oh, hold up, actually, this is continuous. So here, and then I would have a little hole here denoted by the 0, and then I would start again at some point, and then I would have I can have my parabola or something like that, and it goes down. So here, let me erase this. Kind of messy. So this is an example of a jump discontinuity. And what this is again, I have this is my linear portion, or this is a piecewise function total. So let me write this down. Piecewise function. And then what we have is we have a jump discontinuity. So what we have is at this point specifically, there's a hole, but it jumps towards this function here. So I said that this was at x equals 3. So this would be an example of a jump discontinuity at x equals 3, because I have a function here. It's negative 2x. This is, let's see, this is negative 2x here. And then this would be, I don't know, negative x squared. I'll just use negative x squared for example. And like it's definitely translated to something, but I'm not going to calculate it because it's just sketched. But what this is, again, I have negative 2x all the way up to this x equals 3 point here, but then my function is going to jump, and it's going to switch to another function. So it's going to switch to a quadratic function, and it's going to go, if x is greater than 3, like let's say, let's extend this function, we have x equals maybe like 5 here. So at x equals 5, it's going to be part of this x squared function. So we can define that as well. So again, jumping discontinuity is kind of, I'm going to define it as it's kind of like a removable discontinuity, but it actually has a defined value. So it's removable discontinuity. However, f of x is defined. F of x is defined at a specific value, but it's not a value that you're expecting, because if you think about it, you're expecting a 0 here. You have negative 2x is going towards 3. It's going towards x equals 3 here, and it's going to head towards 0, but it's at x equals 3, it's just going to be jumped towards this other function here. So it's desired value, which should be y equals 0 in this case, but it's going to jump, and it's going to be like y equals, I don't know here, negative some value here. So it's f of x is still defined at a specific value, but it's not an expected value. So not expected value, but there's a jump. I'm gonna say there is a jump, and what I'm trying to do is I'm trying to use less kind of mathematical kind of terms just to help you understand all of this, because this stuff is pretty abstract. Like, you're talking about like functions and x's and continuity, and all this stuff is not very, very concrete. You don't see this in the real life. So again, I'm like, if we use lingo that's not like mathematical per se, it might be easier for us to understand what's happening in these functions. So it's kind of, these are the kind of the three types of discontinuities we have. So I'm just gonna do a little review. Again, we talked about continuity first. So again, f of x is continuous at any point. So if you sub in any x values in a function, you're going to get a defined y. So it's continuous at every point in this case. It could be or at some points, as if it's defined. You have f of x is discontinuous at specific points, and we talked about three different, and I'll highlight these. We have three different types of discontinuity. So again, we have infinite discontinuity, which usually exists in the form of an asymptote. We have here a removable discontinuity, so a hole in our function. F of x does not have a defined value, so f of x is undefined at a specific x value. And then we have a jump discontinuity. So what that is again, it's kind of like a removable discontinuity, but what it is that f of x is actually defined, but it's not defined at its expected value of that previous function. The function actually jumps, and its f of x is defined at another place, at another y value that's not as expected, hence why there's a jump in our graph. And we kind of explain this over here with this is a linear kind of expression here, heading towards x equals 3, and then it switches to a quadratic equation. It could switch to any other function as well, but in this case it was quadratic for example 6. So that's kind of the types of that's kind of the concept of continuity and discontinuity. And what we're gonna do is we're gonna do some practice problems here, just to kind of help us figure out what type of how to reinforce this concept, and to kind of be more familiar with what continuity is. So I'll make some space here, and we can write the answers down here. So question 1 says, determine if each function is continuous at a given x value. If not continuous, classify each discontinuity. So we kind of looked at question 1 already, and it says here f of x equals, and it gives you I'm going to rewrite this rational expression down. So this is x divided by x squared plus 3x, and this is nice because they actually give you the x values, which is -3 and 0, but we actually don't need to, because what we can do is we can actually find that out graphically, or we can actually look at the graph and find out what happens here. So as you can see, we have a rational expression here. This is a vertical asymptote. So again, this is things you're familiar with. So this is vocabulary you're familiar with. So this is a vertical asymptote, and it exists at here is x equals -3. And so that's our first kind of thing here. We also have a horizontal. If you look at the graph, we have a horizontal asymptote as well, and this is y equals 0, right? Because look, this function here, if I plugged in a very, very big x value, it's going to head towards 0. It won't touch 0, but it will head towards 0. So we have a horizontal asymptote at y equals 0. And then our last thing here, what's unique about our graph is this little hole here. This hole here represents, again, a removable discontinuity, and this is at x equals 0. So we're going to say this is a hole at x equals 0. So in this question, it's actually, it specifies here at x equals -3 and x equals 0. So all we're going to have to do is define these two things, and we don't have to worry about the horizontal asymptote in this case. So our vertical asymptote is x equals -3. Again, if I look at my graph here, it's heading towards positive infinity, heading towards negative infinity. This is now an infinite discontinuity. So so I can say here, infinite discontinuity. This is infinite discontinuity. So right now I'm just defining these discontinuities. I'm classifying them as if it's infinite, jump, or removable, and that's all I'm doing here. If we have a hole, and we have here a hole at x equals 0. If we have a hole at x equals 0, this is an example of it could be either a removable or a jump discontinuity. But in this case, if I had a jump discontinuity, it would have my f of x is defined at x equals 0. add in unexpected values. So again, expected value here, I would say to be like, I would guess it's half, because it's kind of in between 1 and 2 in this case for y equals half. But in this case, if you subbed in x equals 0 for the function, you won't get it. You won't get a value here. And we can actually check this algebraically if we wanted to, and I'll show you that. I'll show you how we do that. But I'm gonna classify this. This is a removable discontinuity. Removable discontinuity. Okay, so and you can be like, okay, that's sweet. Okay, so we can solve it graphically, but how do I solve it algebraically? And we'll get to some examples in at 3 and 4, but let's just do 1 and 2 first, and I'll show you how we can do this graphically. Oh, sorry, algebraically. My bad. So this is question 1. Sweet. And this is question 2. So question 2, if you look over here, question 2, it gives you another piecewise function. It gives you here at f of x equals -2. When x is less than or equal to 3, and the f of x here is x minus 5 at x when x is greater than 3. And what they did was they plotted it out, which is really, really nice of them. But what we can do is I'm going to write this down first, and then we can figure it out. So this is f of x equals, and then you have two things. You have -2 at x is less than or equal to 3, and then you have here x minus 5 at x is greater than 3. And it's asking at x equals 3, which is really, really nice of them because they tell you where it is. So at x equals 3, if you look at it in terms of graphically, it's at this point here. So if you think about it, if you plugged in x equals 3 for this function, it's going to equal -2, right? Because it's going to follow this rule here. It's going to follow this top here rule here, because as it says here, if x is equal to 3, we're going to follow this function, which is simply just -2, and this is what it's -2 here shown graphically. So at this point, it's actually continuous, because I have a defined value for a specific x value. So in this case, is x equals 3. So at x equals 3, it is continuous. So there are no discontinuities in this function. And again, we can check these algebraically by plugging in this 3 into our function here. It's going to give us -2. Because in this case, if x equals less than or equal to 3, it's always going to be -2, as depicted by this horizontal line. So we're going to move on. Let's move on to question 3 here. So question here, again, they don't give you the graph now, which sucks because we can't graphically tell whether or not there is a infinite kind of discontinuity, a removable or a jump discontinuity. But what we can do is we can actually do this algebraically, and I'll show you how we can do that. So this is f of x, equals, this is x plus 1 all over x squared plus 2x plus 2. And what we can do with this function, and it tells you at x equals -3, which is really, really nice. And what we can do is we can actually go over this. This is a rational expression, and we're basically very, very familiar with this already. I'll just write x equals 3 as well. And we're familiar with the rational expressions already. And what we can do is we can actually, if we want to simplify this rational expression, what we can do is we can factor this this denominator out. So let's do that. So if we factor this out, we're going to get, if you remember from kind of like factoring by simply by visualization, what you're going to get is you get two factors. Again, it's just a review of grade of sophomore math. But what we can do is we have this a times c value, which is 1 here times 2. It has to sum to 2 here. So in this case, what we have here is we have x plus 3 and x minus 1. That will give us and that will give us kind of our factor here. Let me just double check that for us. So, oh no, sorry, it says, oh no, this is actually not factorable. I just realized, because if I did x plus 1 and times, oh, this is -3, sorry. If I did 1 times 2 here, it's nothing's gonna act 2. So I actually can't factor this. So never mind. But so if I can't factor and simplify, what I can do is, if I'm given a specific x value here, if I can't simplify the function, I would just have to plug my function in. So let's just plug in -3 into this algebraic equation. So it's -3 plus 1 divided by this -3 squared plus 2 times -3 plus 2. So what my thinking there was, I was trying to factor out this expression here so I can simplify this function. So when I plug this in, it would be a bit easier. And you can see if maybe we can actually solve for some vertical asymptotes in the denominator. But in this case, it doesn't work out. So that's okay if it's not factorable. So -3, and again, I'm taking out my calculator. So -3 plus 1 obviously is -2. -2, and then our denominator simplifies to, we have -3 squared plus 2 times -3 plus 2. And we have -2 and 5 here. So at x equals -3, so basically here it says at x equals -3, f of x has a defined value of -2 divided over 5, which means this is going to prove that at x equals -3, my function is continuous. It's going to be continuous because, and why do we know it's continuous? We know that because it has a defined value, and we solved for this defined value because I know here f of x, f at -3 equals -2 over 5. So it has a defined value. It didn't give me a math error, didn't give me something that's heading towards infinity. I'm not dividing by 0. These are all mathematical operations that we can do. So f at -3 equals -2 over 5 is a defined value. Therefore, x equals -3 is indeed continuous. So let's move on. Let's move on to question 4 here. So question 4. So question 4, again, f of x. F of x here, we have here x plus 2, and we have x squared minus 4. And it gives us our x values here at x equals, I'm going to say plus and minus 2, just because I'm going to simplify it a bit more. But I'm sure you're already familiar with this notation through quadratic formula or something like that. So this is plus 2 and -2 as well. So again, what we can do is we can just simply sub in our x values here, but I'm going to try to factor, and I know I could factor this function out because if I look at my denominator, I have a difference of squares, right? So we're going back to, this is now back to your previous math courses. So we have x plus 2 at the top, and that doesn't change, but we have here, this is x plus 2 and x minus 2, right? And we know that because this is x squared minus 4. So I can just kind of think of it as an imaginary square root, and I can square root x squared, so it becomes x. Square root by -4 here, in this case, not -4, 4 here, I get 2 and -2. So that's kind of how I factor out my my difference of squares. And what we can do now is we can actually simplify this. And I'm going to do some blue because this part might get confusing. But we have x plus 2 at the top, and we have x plus 2 times x minus 2 at the bottom. And what we can do is we can actually cross these two guys out. And when we cross these two expressions out, we have to take a note here, and we have to say here that x cannot be -2. And why? So if I didn't cross these out and I subbed in -2 into my calculator, I would still get a math error, right? Again, if I sub in -2 at this point, at -2 here, this becomes -4, which is fine. But at -2 here, -2 plus 2 equals 0. Anything times 0 is 0, and we're still dividing by 0. So I just have to take a note here that x equals -2. That it cannot be -2. And every time we do this, if we end up factoring a common term between if we end up crossing out a term between the numerator and the denominator, and I state it here, this is this is a removable discontinuity. And this is my little hole here. So I'm going to say hole. So once we have that, what we can do is I can do one. I basically have nothing. So I have 1 over x minus 2 is my final function. And again, I've already dealt with x minus 2. Can I deal with x equals positive 2 in this case? If I sub in 2 in here, I'm going to get 1 equals 0, which means I'm dividing by 0. Every time I divide by 0, if I get something like this, this is, you can think of it as, this function looks awfully familiar. I'm going to do some red with our rational expression as we did before, like 1 over x, right? So kind of the little squiggly lines that we looked at the top here. So it looks awfully like this one, but it's probably, again, it's translated 2 units to the right, and we know about transformations already. So because it awfully looks like that, we have, again, so at x equals positive 2, so at, I'm going to do this in blue as well. So at x equals positive 2, I have an infinite discontinuity. Because it's heading towards infinity. Right? This will be my vertical asymptote. You can think of it as a vertical asymptote at x equals 2. And then, so it would head to positive, and the y value would head to a negative infinity or a positive infinity, depending on what side of the function you're at. And what we have here is, and at x equals negative 2, we actually have a removable discontinuity. And we solve for that with this function here. When we did this crossing out in the numerator with x equals 2 here and x equals 2 here, this gave us a hole in our function. So this was our hole. So that's a removable discontinuity. So that was number 4. And we'll just do a couple more before we move on. Because doing this graphically is much easier, because we can just look at the graph and we can obviously just find out, oh, this is removable, this is jump. But with algebra, it takes a little bit more work, just because we have to, again, sometimes we have to factor, sometimes we have to kind of divide out things in order to make our function simpler before we sub in our x values here. So let's do let's do 5. 5 is quite easy actually, and so 5 here, f of x. And I'm just going to I'm going to crank up the speed here, just because I know some of you might be bored at home already listening to Joey talk for a while. So again, I'm going to crank up the speed, so if you're following along, which is great. But maybe what you could do is you can actually follow along with me as well, and you can kind of challenge yourself. So f of x here is x squared divided by x plus 1, and this is at x equals negative 1. So if I simply just sub in this negative 1 to this denominator here, I'm going to get a 0 value. So it's going to look like I'm dividing by 0, which means you can think of it as this is the definition of an infinite discontinuity. So and we can prove this, right? So we sub in negative 1 for x values, so f at negative 1. So it's negative 1 squared at the top. I'm going to have negative 1 plus 1. Negative 1 squared is 1 divided by 0. So 1 divided by 0, again, I'm going to get an error on my calculator. But again, this is a classic example of what an infinite discontinuity is. Again, it's heading towards infinity, right? So at x equals negative 1, infinite discontinuity. All right. Should be good with that. And then for number 6 here, we have, this is the last one for a question or whatever for the section. We have f of x equals, my parenthesis looks so bad. I never knew how to draw these guys. Not besides the point, but definitely not an artist. I'm negative x squared plus 8x plus minus 16, sorry. This is x is at 3. So we have this function here. We have f of x is negative 2x if x is greater, or sorry, if x is less than 3 in this case. And then if it's equal to or greater than 3, we have this quadratic expression. We have negative x squared plus 8x minus 16. So it's thinking at x equals 3, what happens, right? So and what we can do is we're going to do this algebraically. So how do we do this algebraically? We're going to simply sub in our x equals 3 here to this function. So if I do f of 3, I'll do some black, sorry. F at 3. If f equals 3, what am I following? I am following this function here, correct? I'm following negative, this if I sub in my x value here, because if x equals 3, I'm following the second part here. So this is negative, this is 3 squared plus 8 times 3 minus 16. And that will equal, if I just take out my calculator real quick. So I have negative 3 squared plus 8 times 3 minus 16. I'm going to get negative 1. So f of 3 here equals negative 1. Now, that's my defined value for at x equals 3. But what I'm going to do is I'm going to check if this value matches this top value here. So what if I did? So I'm going to do an aside here. This is f at 3. And I'm going to sub in, use this function here at the top. And you may be asking, why am I doing that? So I'm doing that because I want to check that the expected value is also negative 1. And if the expected value equals negative 1, then the function is continuous. However, if these two numbers don't match, I have something called a jump discontinuity. And that's how we prove that algebraically. So if I plugged in f of at 3 equals this negative 2 times 3 is simply negative 6. So therefore, the expected value for my function here when it was less than 3 was supposed to head to negative 6, but it's going to jump because it's going to be evaluated with this is defined as this function. It's going to jump to negative 1. So if I were to kind of do a little graph here, so this is at x equals 3. So it's supposed to be negative 1. So it was supposed to head to this value here. Sorry. It was supposed to head to this value here, but it's going to jump, and this is negative 1. It's going to jump to negative 6, where it's actually, it's supposed to head to negative 6. I got it confused. So this is negative 6. It's supposed to go towards this point here, negative 6, but the function is going to jump towards negative 1, which is something that's defined here. So this is, and then I would have my whatever parabola or something like that, because it's going to open down because it's negative x squared. But that's not the point. We have a removable discontinuity here, but it's going to actually, instead of a removable, specifically it's a jump discontinuity because the function is defined at 3. It's going to be defined as negative 1, right? So we have this function here. It's going to prove that this is a jump discontinuity. So at x equals 3, it's going to be a jump discontinuity. And these are the ones that I find that take the most amount of work, because what we have to do is we have to sub this in algebraically twice to be able to figure out whether or not it's a jump discontinuity. Where, for example, infinite discontinuity is a bit easier to algebraically prove because you just have to find out if you get 0 in the denominator. And then for removable ones, it is simply if you have a numerator that's common with a denominator, and if you cross something out, you're going to get a hole in your function. So that's a bit easier to prove. I find that with jump discontinuity, I have to do a little bit more work just because I have to sub in the value twice to figure out whether or not to prove if I have indeed a jump discontinuity or not. Sweet. So this here is a new question. So it says determine if each function is continuous. If not, find the location and classify each discontinuity. So it's asking us to prove now, to prove which x value. So they're not going to give you x values anymore, and we're actually kind of used to that because because that's what we were doing here. Because what we did, for example, in this question here, I didn't need to know that x equals plus or minus 2, because if we did a difference of squares here, we could actually simplify this denominator here. So we actually didn't need our x values. So these questions are going to look awfully the same, but it's a bit slightly more challenging because there's no kind of guide to see which x values you actually have to check. So we have to determine that check for us. So this is 7. This is f of x equals x, or sorry, this is negative x over 2x plus 2x plus 1. 2x squared, sorry, here. So this is, I have, again, a rational expression in this case. I'm not given the graph, so that's unfortunate, but I am given the function. So x here, I can't do anything here, but can I do something with this bottom part? Can I factor it? Let's check. So I have 2x squared plus 2x plus 1. If I multiply this a and the c value, I'm going to do a little aside here. I'm going to get a times c here equals 2, and I have to sum, so product is 2. I have to sum to 2. Can I do that? Let's think. If I have product of 2 and has to sum to 2, my factors of 2 are simply just plus or minus 1 and 2, which means I actually can't get a sum of 2. So the bottom part here, it's not factorable. So that's unfortunate. And you can check here with your, if you do the quadratic formula and whatnot, you sub these points in. Let me do that check actually. So I have a function that has a value of 2, and 1. It's going to give me, yes, exactly, it's going to give me an imaginary roots, which means I don't have a defined x value for my denominator. So if I can't do that, then what I can do is I can actually let's just sub in a negative value, and let's just sub in a positive value to see if this function actually gives you a defined value. So let's think of this is positive 3. So let's define, so this is negative 3 over 2 times 3 squared plus 2 times 3 plus 1. I'll erase this, I'll center this as well. This is 3 here. And let's just do a little check on my calculator. So this would be equal negative 3 over, so this is 2 times 3 squared plus 2 times 3 plus 1. So it's going to equal 25, which means indeed I get some sort of expected value, which is great. So let's check a negative number right now, because the negative might give me, basically I'm trying to prove here, does 2x squared plus 2x plus 1 ever reach 0? That's what I'm trying to prove here. Does 2x squared plus 2x plus 1 equals 0? And we could actually solve for this. So actually, let's do this real quick instead of trial and error, because that might be a bit more tedious. So 2x squared plus 2x, we're going to move 1 to the right side, so I'm going to get negative 1. I could common factor out this x to get 2. I have 2x plus 2 equals negative 1. And now what I can do is I can actually solve this, right? Because there's 2 values here, and this doesn't equal 0, and we know that it was given our imaginary roots in the first place. So I can just erase this. It's just a little check. But if let's plug in a negative number just to reinforce this concept. So this is negative 3. So this is minus 3 at the top. Divide 2 times negative 3 squared plus 2 times negative 3 plus 1 equals, so I have negative 3 on the top again, minus, this is negative 3 times 2 times, let's do 2 times negative 3 squared plus 2 times negative 3 plus 1. You get 13 at the bottom. The two negatives cancel out, I get a positive number, so 3 over 13. So a little check states that my function here is I have a defined value for a positive and negative number. But what if it was 0? So if I plugged in x equals 0, and I can just do this actually just visually. If x equals 0 in this case, the top would be 0. So anything times, it doesn't matter what my denominator is. If I plugged in 0 in this case, it actually equals 1. So 0 divided by 1 is 0. It's still a defined value. It's just 0, right? Which means it's this function here. I can conclude that this function is therefore function is continuous. Is continuous. And what we did and how we proved that was we did a little guess and check. We did a little guess and check of a positive integer, a negative integer, and obviously 0. Because 0 in this case, would give me a still a defined value of 0, but it will give me, but again, it's still continuous, right? It doesn't, I don't have some sort of I don't have a I don't, yeah, I have a specific value for every assigned x, which is great. Let's check. Let's just do one more, or maybe two more, depending on time. But we have here f of x equals, it's x divided by x squared plus 6x plus 9. And what we have here at the bottom is I have something that's factorable. And I know it's because I know that this is a perfect square trinomial. How do I know that? If you think back to, again, your previous math classes, I have here, if you remember, I'll just do a little side here. You have some form of, this is x squared plus, and then it would be 2 times c plus c squared, where c here is your root. So in this case, I would have, every time you get this, you get x plus c and x plus c. So, or you can say it's x plus c squared. So where c is your kind of your root, or whatever number you have here. So in this case, if you were to factor this out, I have here, and simplify this x, so it's x divided by x squared plus 6x plus 9. What's the square root of 9? It is simply 3. 3 times 2 equals 6. So I confirmed that I do have a perfect square trinomial, which means I have x plus 3 in my denominator. So I have x divided by x plus 3 squared. Now it's asking, is the function continuous? So let me set, if I want to prove discontinuity, I'm going to set my function here. I'll set my denominator to 0. So if x plus 3 squared, I'm going to set it to 0. And let's see what happens. So if I square root both sides, I'm going to get this. I just did a little imaginary square root here and square root here. Square root of 0 is still 0. X plus 3, I'm going to move 3 to the other side. X equals -3. So x equals -3, it will make my function 0, right? Therefore, if I plugged in -3 into this function here, I'm going to get, let's see what I get. So it's going to, actually I'll still do this in black. So it equals, again, -3 at the top, divided by, I have -3 plus 3 squared equals -3 here, divided by -3 plus 3 is 0. 0 squared is 0, right? So again, I'm running out of space here. So I'm getting, again, a number or a variable divided by 0 here, which doesn't make sense. Again, this is like another classic example of an infinite discontinuity. And this would be at x equals -3. So again, just the rational expression where I factor out the denominator and set it to 0 to figure out whether or not I have to prove if I have a discontinuity. Either it could be infinite, it could be it might be removable, depending if I factored out something from the numerator here, it could be removable. In this case, I just set it to 0 to figure out if it had if it did actually give me a specific x value, and it did. So therefore, I have a infinite discontinuity. I think I have time for one more, so let's do one more. Because why not? On this 10 a.m. Eastern time. This is Thursday morning. So again, we have f of x equals, we have x squared plus 4x plus 3 here in this case, and that's x plus 3 at the bottom. So what we can do here, we're not given an x value, but what we can do is we can actually, let's factor out the top. So we have 1 plus 3, with 1 times 3, my product has to be 3 here in this case. It says sum to 4. So my two values here in this case are 1 and 3, right? Because 1 times 3 is 3, 1 plus 3 is 4. So 1 and 3 factor out. So those are my roots, which means therefore I have x plus 1 in this case, and then x plus 3 at the top. And I have x plus 3 at the bottom here. As you can see, what we can do is we can actually cross out these roots, because I have something that's common between the numerator and denominator, so I can cross these out. But then I have to write my little exception here, right? I have to write that. Oh, you didn't see this. It's covered by my face, sorry. Product is sum, and product here is 3, sum is 4. And again, because I crossed out this x equals 3, I have to write x here cannot be -3 here, right? And again, this is just a classic example of a removable discontinuity. Every time I cross something out in the numerator and denominator, I get a removable discontinuity. This actually just factors out to x. This works out to x plus 1, but it doesn't really matter. The question's asking us to figure out if it's discontinuous. So what we can say, therefore, we have this because we crossed out something from the numerator and the denominator. This is a removable discontinuity at x equals -3. So let's just review what we did today. In this past hour, I kind of introduced you to what we're doing in pre-calculus. And we were starting with our unit of functions first. So let's scroll all the way up and let's see what we did today. So again, we did here, we figured out, we defined what continuity is. Again, if f of x is continuous at any point or at a specific point of x. So for every x point, there was a defined y value. That's kind of the definition of continuity, or in our sense. We have discontinuity. So at what points of x is discontinuous at a function. So we define this, right? We have 3 types of discontinuity. We have infinite discontinuity. So again, if the function heads to positive infinity or negative infinity, or what we can say here algebraically, and I said we were going to do this before, but we define this as if it was anything divided by 0. If 1 divided by 0, or maybe I'll just do c divided by 0, where c is any real number, any real number. I'm just gonna do any real number. C is a real number. If or anything divided by 0 would algebraically give me an infinite discontinuity. Removable discontinuity simply is a hole in our function. So again, algebraically, like I said, if we were to show this algebraically, it's something if I'm crossing out something from the numerator and denominator, or I can say I have a restriction. If I'm restricting my x value here, in this case, I have a removable discontinuity. And again, a jump discontinuity is a removable discontinuity. However, f of x is defined at a specific value. So like we did our example with the jump discontinuity was over here, right? We tested here x equals 3 for both of these functions of -2x and negative x squared plus 8x plus negative x squared plus 8x minus 16. We plugged in 3 for our defined case, obviously, and we got -1. And then we had an expected value. So if f of 3 at -1, if our -1 was also at f of 3 for this function as well, then the function is continuous because they both kind of join together. But because these two are different y values, f of 3 is -1 in this case, and f of 3 is -6 in this case, there is a jump discontinuity, and I kind of graphically showed that over there. So that's kind of our lesson for today, our lesson on continuity and removable and kind of different types of discontinuity. What we're going to do probably next lesson is we're going to talk about extreme increase, decrease. We're going to talk about relative minimums, relative maximums in specific functions, and kind of intervals of increasing or decreasing. So stay tuned for that. And as always, thank you for watching.